This is Dr. Anthony Revis, and this is SVSU, General Chemistry 111, Chapter 4, Lecture 2. That's Lecture 2 of Chapter 4. We will cover writing and balancing chemical equations, classification of chemical reactions, reaction stoichiometry. We will also look at reaction yields and quantitative chemical analysis. These topics will be covered, however, they might not be covered in this order. In this chapter, we will focus our attention on the concept of limiting reactants and how to carry out chemical transformations involving grams, moles, and understandings of mole-mole ratio and their impact on such calculations. So let's start the lecture by a recap of what a balanced chemical equation is and what we use a balanced chemical equation for. A process in which one or more substance is changed into one or more new substance is a chemical reaction. It is expressed in a balanced chemical equation. So when we look at a balanced chemical equation, and balance is a key term to consider, the equation must be balanced. When we look at a balanced chemical equation, we get an understanding of the type of reactions that we're carrying out and the types of products we're going to get at the end of that reaction. In a balanced chemical equation, we have reactants on the left side and products on the right side. We might also have energy on the left side if it's endothermic process, and energy on the right side if it's an exothermic process. So we have these products and reactants, and products interacting in a chemical equation. And that equation must be balanced. We show you an example of a balanced chemical equation of magnesium plus oxygen in a combination reaction, a synthesis reaction, to yield magnesium oxide. We note that the atoms are balanced. 2 atoms of magnesium plus 1 atom of oxygen. 2 atoms of magnesium oxide are formed, or 2 moles, 1 mole to form 2 moles of magnesium oxide formed. Now, the quantity of product formed is limited by one of the reactants, and that reactant is called the limiting reactant. You will also hear the term limiting reagent used. So occasionally you'll hear limiting reagent instead of limiting reactant. It means the exact same thing. So to understand the concept of what a limiting reactant is, let's make a sandwich. So, one sandwich requires 2 slices of bread for every 1 slice of cheese. That's a sandwich. 1 sandwich, 2 slices of bread, 1 slice of cheese. That is the stoichiometry of this process, of this sandwich reaction. The stoichiometry is 1 sandwich per every 2 slices of bread, or 1 sandwich per every 1 slice of cheese, or 2 slices of bread per every 1 slice of cheese, or 1 slice of cheese per every 2 slices of bread. That is how the stoichiometry is defined. Stoichiometry involves the use of coefficients in front of the reactants and products to balance the atoms on both sides of the reaction equation. So let's say we have 28 slices of bread and 11 slices of cheese. The question would be, how many sandwiches can we make, and are there any materials left over? We can make 11 sandwiches given the 28 slices of bread and 11 slices of cheese. But when we make that, we find that we have 6 slices of bread left over. Therefore, the limiting reagent, or the limiting ingredient, is the number of cheese slices. In other words, we can only make as many sandwiches as the slices of cheese will allow. So the cheese in our example would be the limiting reactant, and the bread would be in excess. We'd have excess bread or leftover bread, 6 slices left over, and we will have consumed all of the cheese. A limiting reactant in a balanced chemical equation works in a similar fashion. A limiting reactant in a chemical reaction is a substance that runs out first. When it runs out, that limits the amount of product that can be obtained. When that happens, the reaction stops. So when that reactant runs out, typically there is another reactant remaining which would be in excess. So again, the reactant that's consumed first would be the limiting reactant. The reactant that remains would be the excess reactant. Be reminded again that limiting reactant is the same as limiting reagent, and excess reactant is the same as excess reagent. Some textbooks still will use the term reagent and not reactant, so be aware of that. But they are exactly the same species. So let's work a problem using the concept. Here's the problem. If 3 moles of carbon monoxide and 5 moles of hydrogen are the initial reactants, what is the limiting reactant and how many moles of methanol can be produced according to the equation shown here? Right? The equation has already been balanced, and you can check that balance by noting that we have 1 carbon on the left, 1 carbon on the right, 1 oxygen on the left, 1 oxygen on the right, 4 hydrogens on the left, 4 hydrogens on the right. When you are working a limiting reactant problem, work the problem as if you're solving 2 separate problems. In other words, treat each of the givens as an independent problem. Do not try to work them where they cross each other. It won't happen. You simply want to blindly work through one given, then blindly work through the second given, and then compare the result at the end. Do not try to compare as you're doing the calculation. So what we will do is solve for the amount of methanol formed from each of the givens. First, let's start with hydrogen as a given. Hydrogen has 5 moles. We set hydrogen 5 moles as the given. We then work through a standard mathematical dimensional analysis where we cross-bar 2 mole on the bottom to 1 mole methanol on the top. We carry that through and we obtain 2.50 mole of methanol, which is what will be produced from hydrogen. We then carry out a second dimensional analysis as if it were a completely different problem, starting with 3 mole of carbon monoxide, and we cross hash bar that through with the methanol to get 3.00 moles of methanol. Note the conversion factors in the middle are not used in determining significant figures. We use the given to determine sig figs. Note that the molar ratios make mathematical sense. The cancellation of the units make mathematical sense. Therefore, we have a lot of confidence in our answer. And then we compare these two and we note that the moles of methanol from hydrogen is less than the moles of methanol from carbon monoxide. Therefore, the limiting reactant is hydrogen. because from hydrogen, the least number of moles of methanol is produced. If the least number of moles of methanol is produced, it stands to reason and makes good sense that that's the least number of grams that's produced. So you could actually carry this through where you would calculate the number of grams from the number of moles. Let's work through another problem. When silicon dioxide, sand, and carbon are heated, the products are silicon carbide, SiC, and carbon monoxide. How many grams of carbon monoxide are formed from 70.0 grams of silicon dioxide and 50.0 grams of carbon? Note that it's 70.0, not 70. Neither is it 70 point, but 70.0, which suggests that this problem will have 3 sig figs in its final answer. We show you the balanced equation. We solve this as if it were two completely independent problems with two different givens. We have the given of silicon dioxide. We take the 70 grams of silicon dioxide, cross-hatch grams of silicon dioxide on the bottom, and it goes up to mole. Keep in mind, in this case, we want to know about the grams produced. So we have the moles of silicon dioxide, which we cross-hatch with the proper units on the bottom, and that goes to moles of carbon monoxide because that's the inner conversion factor. Keep in mind when you're working these conversion factor problems that the interconversion between one species, in this case silicon dioxide, to another species, in this case carbon monoxide, occurs by a mole-to-mole ratio. When you're going from one species to the other, the mid-process step is going to be a mole-to-mole conversion. So we make our mole-to-mole conversion. So we cross-hatch down carbon monoxide up to gram carbon monoxide. We calculate it through and we get 65.3 grams of carbon monoxide if we use silicon dioxide as the limiting reagent. Okay? Next, we carry out a completely separate dimensional analysis with carbon. Okay? Start with 50 grams of carbon, cross-hatch down, 12.01 gram on the bottom because that is the allowed mathematical process, gram to mole, then mole to mole, interconversion to carbon monoxide, and we use the molar ratios from the balanced equations. Perhaps I need to reiterate that again. At a mole-to-mole conversion, you use the coefficients in the balanced equation. The coefficients in balanced equations are used for the mole-to-mole conversion. Do not make the mistake of counting the moles within the compound. Okay, the molar ratio within the compound is not used. The molar ratio from the coefficients in the balanced equation are used. So we make the interconversion, we carry it through the grams, and we get more grams using carbon than we do with silicon dioxide. Therefore, carbon is in excess and silicon dioxide is the limiting reactant. So we can only get out as much carbon monoxide as silicon dioxide will allow. Okay? Carbon will be in excess, and we can determine that amount of excess as well, which we will show you how to do in this chapter. Let's do another example. Urea is prepared by reaction of ammonia with carbon dioxide. We show you here the balanced equation. The balanced equation allows us to know the stoichiometry. The stoichiometry of the balanced equation is where we use these coefficients in the mole-mole conversion factors. In one process, 637.2 grams of ammonia were treated. Okay. Which of the two reactants is the limiting reactant? Calculate the mass formed as a second step, and how much excess reactant in grams is left at the end of the reaction. So, we will treat this as if we are working two separate problems. Again, we start with the givens and we treat those givens as two separate problems. And at the end of the process, we compare to determine the limiting reactant. And if we know the limiting reactant, we can also determine which one is in excess and by how much. So, let's treat 637.2 grams of ammonia with 1142 grams of carbon dioxide and determine the limiting reactant, the excess reactant, and how much excess there is. We'll treat this as two separate problems. Let's start with using the ammonia. When we take the ammonia as a given, we set up a dimensional analysis process, which you know how to do now. Gram on the bottom, mole on the top. Then we do an interconversion because we're going from one species to the other. So we'll need a mole-mole interconversion. And in a mole-mole interconversion, we look at the balance equation to determine the moles that we write in this equation. And we get 18.71 moles of urea. Then we treat the second problem. It's like two separate problems with the 1,142 grams of carbon dioxide. We carry this through a reasonable dimensional analysis that's sound in terms of the math. We do an interconversion, and we note that in the balance equation, it's a 1-to-1 relationship of urea to carbon dioxide. We carry the calculation through, and we get 25.95 moles because we have 4 sig figs in our starting given. We'll need 4 sig figs in the final. It follows then that ammonia must be the limiting reactant since we get less urea from that process than we get from using carbon dioxide as the limiting reactant. So now that we know how many moles we produce, we can carry out a dimensional analysis conversion to the number of grams of urea we produce. Because actually in a plant and in manufacturing, it's the pounds, if you will, or the kilograms. So let's prepare for the number of grams that we produce from 18.71 moles. So we take the 18.71 moles, we do a dimensional analysis where we use gram per mole as the conversion factor because gram per mole will allow us to get to grams from moles. We do the conversion and we obtain 11.24 grams of urea. Finally, we can determine how much excess we have. We determine the excess by going back and starting with the limiting reactant. Once you've determined the limiting reactant, it's important to recognize that the calculations going forward then use it to determine the mass and moles of any other species in the process. So next, we want to determine how much excess reagent is left at the end of the reaction. We do this by first determining the amount of carbon dioxide actually reacted. The amount of carbon dioxide originally reacted is based upon the limiting reactant. So we take our limiting reactant and we process it through a dimensional analysis. The very first step is an interconversion between mole to mole. Then the next step is a conversion of mole to gram. which gives us 823.4 grams of carbon dioxide. We have 4 sig figs in our answer because our starting material had 4 sig figs. Okay? So now, the amount of carbon dioxide remaining in excess is the difference between the initial amount, 1,142 grams, and the amount reacted, 823.4 grams. We take the difference between these numbers and we get 319 grams. Notice that the number of sig figs in this subtraction problem is done in this way because we align the decimals, and when we align the decimals and truncate to the nearest placeholder to the decimal, that placeholder would be 2. Okay? So you will want to go back and review your sig fig rules for addition and subtraction. In subtraction and addition, we align the decimals and we truncate to the shortest number, that is, the value that's closest to the decimal. In this case, it's the 2 in 1,142. A very important concept in any research laboratory or in production is the reaction yield. Theoretical yield is the amount of product that would result if all the limiting reactant were used up. If all the limiting reactant were reacted, that would be your theoretical yield. The actual yield is the amount of product actually obtained from a reaction. How much did you actually get out of your reaction vessel in the laboratory or dig from the reactor in the plant? So when we want to get the percent yield in, we would take the actual and divide it by the theoretical times 100, like we would do any percentage, following the basic rules of math. So we can determine the percent yield of our reactions. It's important, however, to remember that in any of these reactions, the chemical equation must be balanced. That's rule number 1. Then the limiting reactant is determined by the reactant that yields the fewest number of moles, which is proportional to the number of grams. So let's do an example. Let's work a problem. Titanium is a material used in rockets and aircrafts and jets. We have a balanced reaction between titanium tetrachloride and magnesium. This reaction yields titanium and magnesium chloride. In a certain industrial operation, it was found that 3.54 times 10 to the 7 grams of TiCl4 is reacted with 1.13 times 10 to the 7 grams of magnesium. So we have titanium tetrachloride, which is what is typically referred to, and magnesium. They react together, and we want to calculate the theoretical yield of titanium in grams. So we essentially know we have to get to grams in this. So we want to then calculate the percent yield of this. So in a certain industrial operation, we have 3.54 times 10 to the 7 grams of titanium tetrachloride, and it's reacted with 1.13 times 10 to the 7 gram of magnesium. Two things we want to do with this in this problem is calculate theoretical yield, and then we want to calculate the percent yield. So there's two things. You have the theoretical yield and you have a percent yield, and we need to calculate both of those in this problem. To do this, we treat this as two separate problems initially because we want to determine the limiting reactant. But the first thing we must do is be sure that the equation is balanced. We check that and we know that we have a balanced equation. Therefore, we can proceed to use both the givens and treat them as two independent problems solve for a value of moles that we can convert to grams, compare the two, and then we can determine which is the limiting reactant, and then use that to drive the rest of our calculations. So let's do it then. Starting with titanium, we have 3.54 times 10 to the 7 gram. We write that as our given. We do the dimensional analysis. We carry it through from gram to mole. Then mole titanium is cross-hashed through to moles of titanium. And we get 1.87 times 10 to the 5 moles of titanium. Next, we want to get the moles of titanium obtained from magnesium. So we start with magnesium given. We put the right units on the bottom, gram, because that's what's mathematically sound, over the moles. Then we do mole to mole, and we see mole to mole. That means that's an interconversion factor. And we get the 1 over 2 from the balanced equation, as we did getting the 1 over 1 when we use titanium tetrachloride from the balanced equation. So we get these two values. And what we observe is that the 1.87 times 10 to the 5 mole titanium is the limiting reactant. Now, you want to keep in mind that in working these through and teaching this, the limiting reactant in both these, or actually in the 3 of these, have been the first material. That is not always the case. That just happens to be the case when preparing these slides. So we have titanium tetrachloride is a limiting reactant, and magnesium's in excess. So we have that. So now we can take this further to determine the mass of Ti formed, okay, based on the limiting moles. So we take the limiting moles of Ti, we carry it through a conversion to grams using the molar mass of Ti, which is 47.88. And we carry that through and we get 8.95 times 10 to the 6 grams of titanium. We get the 3 sig figs because the starting material has 3 sig figs. So what about the percent yield? We have the mass of Ti. So the percent yield would be the actual divided by the theoretical. We look back at the problem to obtain the actual, and we discovered we had 7.91 times 10 to the 6 grams. And that's divided by the 8.95 times 10 to the 6 times 100 for a reaction yield of 88.4%. So let's recap what we learned in this lecture. We know that a balanced equation is essential to carrying out any chemical reaction process. That balanced equation contains reactants on the left side of the equation and products on the right side of the equation. A limiting reactant will limit the amount of product produced from the balanced equation. That limiting reactant is what runs out first. That limiting reactant stops the reaction. The other reactant is the one in excess. It is called the excess reactant. In the case of the excess reactant, we can calculate at the end of the process just how much excess that is. But in order to do that, we must carry out two-dimensional analysis, where we carry out with each of the givens in the reaction. Then we examine the moles or grams from each of those steps to determine which is the least. And the one that's the least is called the limiting reactant. Now, the limiting reactant is not the product. Be sure that you note that. It's not the product. The limiting reactant is the species that gave the product. When you carry out these calculations for these reactions, you will get the same material out. And that one with the least number of moles or least number of grams will be the limiting reactant. We can use a mole-to-mole interconversion in going from one species to another. The percent yield may be obtained by taking the actual output yield from the reaction, the mass that was output, divided by the theoretical yield. The theoretical yield is calculated using the limiting reactant. We take the actual divided by theoretical times 100 and we get the percent yield. The amount in excess will be the difference between the amount of the excess reagent you started with minus the amount of reagent that was used. And that amount that's used will be based upon the limiting reactant. There you have it. Lecture 2 of Chapter 4. Stoichiometry and chemical reactions.